Good afternoon, everybody. Here is our last podcast of this chapter as we get ready for our finals. I hope you guys have been doing a good job getting prepared in all of your classes, not just in chemistry. So here we're going to talk about Hess's Law. This is going to be a short little podcast. Hess's Law says many reactions occur as a series of steps. And so what it really is a way that you can develop and find an answer, the heat of an equation that's given off when the steps would take a really long time or you're not actually doing the reaction. An example of this would be that we know that carbon can take all kinds of plants and animals and they decompose into carbon that eventually can be pressed down into diamonds. Well, obviously that's not anything that you are doing right in front of you or in the laboratory setting, but maybe you do want to determine the heat of the overall reaction. Well, that's what happens with Hess's Law. So in this example, if I take a look, it says calculate the change in heat for this reaction. So this is my answer. I want to find my change in heat overall for this reaction. Now, in all the other examples that we've been showing you, we've been giving you that. Now, Hess's Law is saying that I can take these bottom three reactions, manipulate them to look like the one that I have starred up here, and when I do that, then I can use the heat of reactions of these individual ones, add them up, and I'm going to get the overall reaction above. So the first thing that I want you guys to do is you want this in the forward reaction the way that it is. So the first thing we're going to look at, I need 2 moles of N2 on the left-hand side as a reactant. So if I look down at this third equation, I can see that here it is, but I do not have 2 moles of it. So just like in math class, if I multiply this by 2, then I need to multiply everything else by 2. So this would become a 6, this would become a 2, and this would become a 4. And just like the energy, I recognize that this is an exothermic reaction, but I also need to multiply that by 2 because I have twice the amount of energy that's going to be released. And a lot of times I like to circle that one because I know that I have that one completed now, and I don't want to do anything else to that. Now I need to have 5 oxygen. So if we take a look at the second one here, I need to have 5 oxygen on the reactant side. Now because I have oxygen in a couple different spots, I might leave that one to last just to see, because right now I have 6 oxygen here and I have 1 oxygen here, so I have 7 on the left-hand side. So let's go on to the next one. It doesn't matter what order we do this in. So I have 2 moles of dinitrogen pentaoxide. So if I look at my equations, I can see that I have dinitrogen pentaoxide right here. However, I have a problem with that. I only have 1 mole of it, and it's on the wrong side of the equation. So I'm just going to flip that. So I'm going to turn that around and write it on the other side and multiply by 2. So I have 2 moles of this nitric acid. Now I'm going to have 4 moles of nitric acid. And I'm going to have 2 moles when I multiply by 2 of my dinitrogen pentaoxide plus 2 moles of water. And when I take my heat of reaction here, what I need to do is I need to flip that. So that's going to make that positive. And I need to multiply by 2, which is what I did. I flipped it, and it went from exothermic to endothermic, and I multiplied by 2. So I'd like to draw a line through this because I am no longer going to be looking at that one. And I now have my dinitrogen pentaoxide in the right form. So the last thing that I have to do now is I have to get back to these 5 oxygen and figure out where that is. So by looking at my other things, I didn't do anything with this equation here. And it looks like if I take and flip this one, then I would have 1 oxygen on the other side, subtract it from the 6 that I have here, and I would have my 5 oxygen. So I don't need to multiply by anything, I just need to flip it. So I'm going to do that. So I'm going to write my 2 waters on the left-hand side. I have my 2 hydrogen plus my oxygen gas. And now I'm going to add everything together. Now, because the arrows are like the equal sign, I have 6 oxygen right here, and I have 1 oxygen right here, which is going to give me my 5 that I need. And then everything else better cancel out so I know that I did it correctly. So I can see that I have 2 hydrogen on the left, 2 hydrogen on the right. I have 4 nitric acid on the left, 4 nitric acid on the right. I have 2 waters on the left. I have 2 waters on the Right. Now I forgot to write down my heat formation on this one, and I flipped it. That's all I did. So instead of this being an exothermic reaction, it's now going to be an endothermic reaction. And I got rid of that equation because I flipped it. So I'm going to take these three numbers right here, and I'm going to add them up, just like I'm going to add up my equation. And when I do that, I'm going to get my resulting answer. So when I take a look at my equations that I have here, I have my 2 nitrogen, I have my 6 oxygen here, plus 1 more over here is going to give me 5 on the left-hand side. And all I have left is my 2 nitrogen moles of dinitrogen pentaoxide. Now I'm going to grab my calculator. I'm going to take 2 times this exothermic reaction plus 2 times 76.6 plus 571.6. Punch that in your calculator and make sure you get the same thing that I did. And it's going to be an endothermic reaction, 28.4 kilojoules of energy that was taken in. So what that's saying is that I didn't actually do this equation in lab, but I manipulated 3 other ones to give me the change in heat of this reaction. That's it. That's Hess's law. So go ahead and try a couple of homework 4. If you have any questions, make sure you bring them to class. I hope that you have a wonderful day. Was I not recording?